I'd like to take a couple minutes and prove Green's theorem. There's three big theorems in this chapter: Green's theorem, Stokes' theorem, and the divergence theorem. Green's theorem being the first of these. And I think it's just important to walk through at least a simplified version of the proof so you get some idea of where this kind of cool and surprising result comes from. So I'm just going to walk through the book on this particular example. So the proof of Green's theorem is straightforward when restricted to special regions. We consider regions R enclosed by a simple closed smooth curve C oriented in a counterclockwise direction. So we're going to go around this direction such that the region can be expressed in two ways. So it can either be described as between an upper and a lower part, or it can be described as being between a right and a left side. So notice, for the sake of these descriptions, that we're going to call this lower part here C1, and we're going to call this upper part C2. And so you could think about C as being C1 plus C2. So under these conditions, we prove the circulation form, not the flux form, but the circulation form of Green's theorem. So remember, the circulation form of Green's theorem says that the line integral around the closed path C is f dx plus g dy equal to the double integral of the partial of g with respect to x minus the partial of f with respect to y, and this is dA. So what we'd like to do to start with is we're just going to focus in on this second part of the double integral, the partial with respect to y. And so we're going to begin with that term, and then once you get the idea for this term, you will pretty easily see how you could work with the partial of g with respect to x term. So we write this double integral as an iterated integral. So we're coming from this picture here on the left, where g1 of x is less than or equal to y is less than or equal to g2 of x. So we're stuck in between this lower and upper curve in the integrals between a and b. Notice that the inner integral partial of f with respect to y gives the antiderivative f of xy. So this is kind of a key result. So notice that if you focus in on just this part here, and assuming we were integrating dy, if you will, that it's like right here, and notice that the antiderivative with respect to y of the partial of f with respect to y would be just f. And so we would take that f and we'd evaluate it at the top point and evaluate it at the bottom point. So it's like, it's a antiderivative of partial of f with respect to y. dy would be f of xy. And here I'm ignoring the constant, and then we would evaluate that from the lower point to the upper point. So we could go from g1 to g2, and so we're going to evaluate here from y equals g1 to y equals g2. And so when you evaluate at g2 here, you're going to get f of x comma g2 of x, and then when you evaluate at g1, you'll get minus f of x comma g1 of x. And all this stuff is still inside the outer integral. So again, what we did was we wrote our double integral as an iterated integral, and then we recognized that this was just the fundamental theorem of calculus in reverse. So boom, we went from a double integral to a single integral, and here we have the difference. So similarly, over the region A to B, the points x, g1 trace out the lower point. So you have the top part is tracing out C1, the lower part, or the second part is tracing out C2, and all this is happening in the positive or counterclockwise direction. So therefore, we get that the double integral of partial of f with respect to y dA is the integral from A to B of f, x comma g2 of x, minus f of x comma g1 of x, all with respect to x, which we could write now as line integrals. And notice that having the negative C2 is the same thing as having a negative line integral, but going in the positive direction. And so here we remember that C1 plus C2 gets us all the way to C. So all this stuff is giving us the negative C. Let's go back up here and check our signs one more time. So notice that C1 is going from A to B, but C2 is going from B to A. That's why we end up having to change the signs of what's going on here. So we get that the double integral is equal to negative the line integral around the closed loop of f dx. We can do something similar with the partial, the double integral of the partial of g with respect to x, where we show that this puppy is equal to the line integral around the closed path of g dy. And so we can combine these two calculations, and we get that the double integral of gx with respect to x minus the partial integral of f, let me say that again. Double integral of the partial of g with respect to x minus the partial of f with respect to y dA is equal to the line integral around the closed path of f dx plus g dy. As mentioned earlier, with a change of notation replacing g by f and f by negative g, the flux form of Green's theorem is obtained. This proof is also completes the list of equivalent properties of conservative fields that we've talked about earlier. From Green's theorem, it follows that if the partial of g with respect to x equals the partial of f with respect to y on a simply connected region, then the vector field f equal to f comma g is conservative. So there you have a little bit of a proof and a conclusion, helping you understand the importance of Green's theorem in its various forms.